What I go do this morning is give you a workshop on AI, on deep learning, and it will be a little bit a special one, because deep learning is now everywhere. We use translation machines. You know that deep learning is something, for the first time in history, we can now recognize by computer. So we can recognize, let's say, pathology in medical images. We can recognize what's wrong. We can recognize also what flower is this, what translated word is this. And we couldn't recognize before. It was very difficult. People tried all kinds of feature methods, etc., complicated things. But now for the first time, we really can recognize. And of course, the best recognizing machine is our brain. We can see, we can listen. And I talk today also a little bit about the relation to the brain. That's why I call it neuromath. And a little bit of mathematics, but a little bit of what happens in the brain and what happens inside these neural networks. And I give a very special lecture. The lecture will be with computer code. So you really see how the computers do this, step by step, slowly, and I explain things, what happens. So a little bit about my background. I'm now emeritus. I retired, and I worked for a long time at Eindhoven University. This is my campus. A bit closer, that's fine. Eindhoven is the high-tech city in the Netherlands. We have even 4 campuses. We have Philips Healthcare, we have ASML, we have the high-tech campus, we have the university campus. 1/3 of all the money in the Netherlands is earned in this city. It's quite impressive. ASML, 37 billion euros profit last year. And my field was quite broad. I trained students in biomedical image analysis. So there was breast cancer detection and lots of it. I'm now retired since a few years, but I'm still quite active because I love to teach. Everyone in his life has to find out what do you like most, and what do you business, academics, and for me, teaching is my hobby. And I'm writing now a book and try to bridge a little bit the deep learning technical side, the computer. And I want to give you this morning a little bit of flavor of that. I did some work on scientific visualization with my team. It was quite nice to work on this visualization. And the heart is beating, so this was 4D, X, Y, Z, and time. We did a lot on brain connectivity. This was the first time we could use an MRI scanner to find the wires in the brain. You see the wires here that connect the left and the right side in the brain. So they're colored in a way that the X, Y, and Z directions, so the 3 directions are red, green, and blue, so you could see a little bit better. But the doctors could interactively, nicely study what is the connection between this, and from your eye to the back of your head, etc. This was a revolution in the field, and I was very happy to be part of it with my field. If we go to computer-aided diagnosis, computer-aided detection, what does it do? It actually finds in medical images some particular things, and it has to learn what these particular things are. So here, for example, you have some beginning of a tumor. It's hardly visible, but you have to find it. And the classical way was to do, well, a whole pipeline. You do pre-processing, that means you get a little bit rid of the noise. If there are some letters in the picture, you remove them. Then you do a segmentation, that means make it into segments. You find the lung fields. And then you do feature extraction. And feature extraction is filtering. You do all kinds of filters that you see, well, are there some lines, some edges, are there some corners, all kinds of little things. And have people, traditionally, we designed these features. So we made them up. We came up with all kinds of, what features could there be? Could there be little lines, or could there be little black-white regions? And today we have deep learning. They learn the features, so we don't have to design them anymore. We can just see, well, what's in the picture, and then you extract some selected features. You say, because if you design 100 features, only 15 may work. So you find out what are the nice ones, and then you filter them, and it turns out that you get a whole cloud of, suppose you have 3 features, 1, 2, 3, and you say, okay, the response of this feature is so strong, and that is so strong. This is what's called a feature space. And I have only 3 here, and computers have, let's say, many more. You can have 100 features, but we cannot see a 100-dimensional field. We can only see 3 dimensions. And all these features are hanging here, and you see there are 2 clouds. And now is the trick for the computer, find the division line between the clouds, so you say, okay, these are the thick ones, and these are the healthy ones. And sometimes this is very easy to do, sometimes it is a little bit curved, etc. And this never worked so well. Here you see some of these features. So this was the classical way to do it. And then we had means to see how well does it work. And this line is, the more it is to the upper left, the better it is. So this blue line is really nice, and this green line is not so good. And it turns out that it was always, not so good. And today, deep learning, it has it almost in the corner. It almost has about 100%. It's even better than humans, and that's why it is so spectacular. Why can it be better than humans? The reason is it learns from so much more. If I have a human, 25 years career, looking at breast cancer, how many cases can he see? Maybe 8,000, 10,000? The computer can see 50,000 in a week. So it is a whole different story. We have so many more data. If we look at translation machines, they do not study one dictionary. No, they study the whole Library of Congress. They study all the European Union documents, you name it. That's exactly what they do. So if we compare now deep learning, first of all, why is it called deep learning? We use neurons, and the neurons are known from the brain. And here we have a whole set of a layer of neurons, another layer of neurons, and all these layers look like in the visual system. If we have the visual system here, this is the eye, there's the optic nerve, and the signal goes to the back of your brain, and here is your visual system. So if I put my hand on the back, I cover about 1/4 of my brain, and 1/4 of my brain is for vision. That's enormous. It means we are visual machines. If there is something visual, I forbid my computers to make textual slides. So bulleted slides, they're out. You should give a picture. A picture tells more than 1,000 words, everybody knows, because we are made for pictures. If you look at the visual system, and if you go from the back, here are the neurons in the eye, you see they first go to the first visual layer, it's called V1. Then it goes to V2, V4, V4, V5. And all these layers we see in the brain, that's exactly what they do in deep learning too. So it's called deep because we have these many layers. And then there is the output layer, and the output layer is, what does the system has to do? Sometimes it has only 2 outputs. It has to say it is sick or healthy. Or it has 4 outputs. Say there's some level, it is a little bit, more, very much, or very high level. Or if it is a recognition system, it has 1,000 outputs. It can recognize if it's a cat, a dog, a horse, a beach, a church, you name it. We all know Google Lens. Google Lens is an application made by Google. It learns from all the images that we show. It has 1 billion outputs. It can recognize 1 billion objects. That's quite impressive. And if we see what these layers do, well, you put in, for example, a face, and you let this system actually learn, and I'm going to explain nicely what this learning is. And you look what has learned after some time. Well, actually, I have to explain what are these blue lines here. These are the connections between the neurons, and these connections can change. They can be strong connections or weak connections. So every blue line has a value. If the value is 0, there is no connection. If the value is 1, there's a very strong connection. If the value is 0.5, 1/2, it's not so strong. And the system learns all these connections. And the modern networks has millions of these connections, so it has to learn a lot. So training a neural networks takes a long time, because you have to learn all these connections, actually one by one. That's why we need so many data. You need to train it and train it and train it. Well, once you have trained it, you're rich, because then you have an expert brain, and then you put in something, and it immediately does something in a millisecond. And then you could put in here your breast cancer image, and it tells immediately what it is. So then you have a trained doctor, and that's highly valuable. Then you can make money. But the training takes time. You need to have the data sets to do the training. And if you look inside, you see here all the first layer networks, and these are simple lines. And suppose I want to detect a little bit more complex in the face, I want to detect a nose, I need 3 lines, because it's a triangle. So if you combine these lines, you get here a little bit more the combination of those, and then you see eyes, nose, ears, and if you combine those, you see a face. And if you combine those, you get a picture with more. So you increase the context. And the stepwise increase in context, that's actually what happens. Well, this is a neuron. Most of you are from the medical field, so you know all this. And a neuron has connections by other neurons. And if a neuron connects here, that's called a synapse. And the synapse in biology, it's a connection. It's like a small mushroom sitting on the cell. And if you learn, it increases in size. It gets just bigger. And that means that the connection gets bigger. And if you forget, it decreases. So that's actually how biology learns. And in a computer, you just make this a higher number. And we used to have neural networks only by 3 layers for about 20 years. And 3 layers didn't do a good job. So you could put in all kinds of images of cats and horses and see what is the output. And it was 75%. And when you go to a hospital and doctor, he said, you want a system that's 75%, everybody said, well, come back when you're better, because this is not good at all. So for many years, we had quite a problem to get all this accepted. And now, we have 94%. And doctors are about 90%, 92%. So it's quite impressive. Sometimes doctors are better. It's a little bit in the balance, but quickly we go, because we have all these things. And if you see these neural networks, that you recognize all these layers one by one. And I go explain a little bit more in detail what these layers actually do. And the first one who did this was Alex Grzybski, and this network is called AlexNet. And there was a game at that time. It was called ImageNet Challenge. And they made available 1.4 million images in 1,000 classes. So there were horses, and they invited the whole world, please write a system and do the best classification. And hundreds of people started to do this, and the winner was Alex Grzybski. And he was at once from 75% to 94%. It was an amazing step. So everybody then said, wow, this is the big boom. And this happens about 10 years ago. So it is a very young technology. But now everybody is jumping on it. And it's not only for images, but it's also for recognizing speech, electronic patient records, chemical data. You can put in all kinds of DNA data. So it's everywhere. And if you put in something in this network, all these layers do their calculations, and then you get something out. But when you get something out, it may be wrong that you put in, for example, written digits, and you have small letters. You say, okay, I write a 6, and it should also say it is a 6. But it says it's a 7, and that's of course wrong. Well, how much wrong? It's 1 wrong. Then you go tune, you turn on the knobs of all these connections, and you tune just as long until it says it's a 6. And that turning, that's the learning process. And when it's a 6, you say, okay, then I give the next one. And that's turning the knobs to all these connections. That is error correction or error backpropagation. You begin at the end, turn the knobs, and you go for deeper and deeper backwards. So error backpropagation is the learning project. And that takes quite some time, because you have hundreds of millions of connections sometimes. The key trick. And what makes deep learning networks so essential? If I have a medical image here and you see a catheter, well, everybody sees the catheter here. But if I only see a local area, and that was what computers were actually seeing, they saw a couple of pixels and not so much around it, the computer was actually see a keyhole image. But if I give it context, now you immediately see, hey, there's nothing to see here, but if I have the big surroundings, and that's exactly what these deeper layers do, they see the big surroundings. So now we can see much more than just processing in a pixel, we can process the context. And this has been a study for a long time, since the 30s already, that psychologists were wondering, how is it come that all these circular balls, they only differ in color, that they form lines in my brain? Because I see horizontal structures. And this is disconnected, but everybody sees, okay, it must be connected. Maybe there's something in front of it. So our brain can fill it in, but only because there is context. Well, this is a psychology that's called Gestalt, and deep learning and Gestalt are very much related. And why is it so interesting to look at the brain? If we look at these big data centers that do all this learning, and Google has these big centers, Microsoft, Facebook, you name it, they use an amazing amount of power. It goes in the megawatts, 10 to 100 megawatts. They have cooling towers on top. We have quite a few in the Netherlands, and everybody is concerned they eat so much energy that there's hardly any left over for the normal population. So we have a little bit worries, why is it so big? And inside we have all these storage, etc. But my brain is doing the same thing, recognizing, storing. And this small brain uses only 25 watts. And that's a lot less. It's not 10% less. No, it is orders of magnitudes less. And if I look at the speed of my computer, for example, my computer is 3 gigahertz. That means 3 trillion times per second it can do a calculation. But my neurons are 2 kilohertz or 6 kilohertz. That's 6,000 and not 6 trillion. So the difference is not just small. That means we have only just begun. We have to learn a lot from the brain. Why is the brain so incredibly energy efficient? And in the last hour of my talk, I'm going to talk specifically on this. We have discovered modern brain science is just as fascinating as modern computer science. But many people don't know all these discoveries that all these biologists do. They can now image the brain on a nanoscale, almost the smallest things we can see. And I'm going to show you a little bit what we discovered in the brain. The retina is not a regular camera at all. The brain is doing geometry. That's a little bit for the technical side. And we have all these energy-saving strategies. So if we look at the brain, it was pioneered by Hubel and Wiesel. They got a Nobel Prize many years ago. And they looked into great detail what all these cells are doing. So they made fantastic discoveries. And they found out that the brain has all these layers. The brain has all these nice filters. The processing is done. Here we see V1, V2, V3, all these layers. And it's extremely well known how this is all mapped. So we know the map of the brain. And I go use a language, because there's so many computer languages, that's a little bit more modern than most languages. The language I use is Mathematica, and I go show you a little bit deep learning with this language. And today there are about 200 languages to program a computer. The most used is Python, and we have lots of them. But Mathematica is a little bit more special because it can do better mathematics, and it's more closer to English. It's more easier to understand. So I hope that you, as a medical audience, can also understand a little bit what's coming up. It's already there for 25 years, and it has always been extremely innovative. Most of the innovations in computer science came actually from this company who made it. It's made by an American scientist, Stephen Wolfram. He wrote alone, 29 years old, millions of lines of codes, and he wrote this program. It's a very impressive thing. And I'm a little bit amazed that it is not worldwide used so much, because people stick to the conventional way of using Python, and I think that Mathematica is a little bit, it's more modern. It costs money, and all the other languages are free. And I'm a little bit amazed that people don't want to spend money. It's actually quite cheap. It's only 100 euros a year, and for a student, and for a normal person, 200 euros a year. So it's actually quite cheap, and I think if you need quality, you like a car, like etc. You can have a bike, but okay. This course will not be on how to apply deep learning. So at the beginning I will do a little bit, but more how does it actually really work inside? Can I trust it? If I don't know what happens inside, then how can I ever use it? Because it may be nonsense what it says. Often it's right, but if it goes wrong, how can I repair it? What happens inside? So the philosophy is I go talk in a high-level language, that's the Mathematica, and I present it as a computational essay. So my first hour, I have 3 hours, but I make it a little bit less because we started less, and I'll go slow, so I probably will not talk about everything, but all my code is available for those who want to see it, and you can download it. The first is, how does it actually work? Let's make some networks. Let's play with the networks. We cut them in pieces and put them together again. We call it network surgery. And can we look inside what they actually do? So let's make some photographs for what the networks do when they learn and what happens. And the second hour will be a little bit more technical on what is this self-organization doing, how come it learns. But it also explains you, how come that I learn? What happens when I learn? When I'm a toddler, for the first time, I use a bicycle or whatever. How do I learn all this? And the last will go lessons from the visual system. And this is the website that I made for this workshop. If you look on this website, let's see if it works. You see the announcement, and it's a whole description what actually is coming up. And on the bottom, you see download buttons, and you can download everything that I discuss here. The full code, all the text, all the slides, and you can just have a look. This is on the website of SSIMA.eu. Okay. I think I skipped the questions for now because I end my PowerPoint presentation and I go now to I start now this program that's called Mathematica. And here you see a little bit, I make it bigger. And I go do some age estimation with a famous network. There are many famous networks today, and they all have nice names. This is called VGG16, but I don't know, that's a scientist who made it up. Trained on this, well, this is the name of a big data set. And actually, you can get these networks from a website, It's called the Wolfram Neural Net Repository. And on this, it's from the maker of Wolfram. On this website, you can download all these trained networks for free. So if you need a network that can recognize brain tumors, or you need a network that can recognize language translation, or a network that, you name it, there are about 200 networks. The very famous one, they're all there. So here you see networks for classification. So they do the same as Google Lens. You have networks for about everything, and it's very impressive. I'm going to show you a few. So this is how a computer works. You just say, I want to have a net model, and the name of the net model is this. It's between quotes because it's a name. And now you can see, okay, I download it. And now I have my network, and let's have a look. What is it? And you see lots of layers. Layer 1, layer 2, and they have all names. Convolution layer, ramp convolution layer. Wow, a lot of layers. And it has a beginning and input, and the input is 224 by 224, so that means it's a small image, 224 pixels by 224 pixels. And it's by 3 because it's a color image, red, green, blue. So every pixel has 3 values, red, green, blue. And the output is just one class. And this network estimates the age. So there are many net models. If I ask the computer net model without asking for a question, you get them all. Not so interesting, but you see they all have a name, and you can just very easily read them. And you use HNet by these 2 brackets because what we call in mathematics, it's a function. You have to put in something, a face. So how do I get a face? Okay, let's open a browser window, and I ask for my own name because I want to put my own image in there. Bart Romeny, let's sign in. Let's put some images. Okay, let's pick this image. And what I can do now in Mathematica, I just say, okay, plug this image right in here. And now we can ask the network, process this image and tell your outcome, hey, 65. Well, this is right. This was when I become a pensionado. I was 65. I'm now a little bit older. No, the recognition is done on my computer because this network is in my computer. So this whole network, it's called a net chain. It has all these layers as a chain. The image goes in, and all the processing has been done. Check, 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 check. And at the end, it says 65. This is real time. This is exactly what happened. We can... Of course. Then I go find... Is it right like this, Brookstein? Okay, there we go. I delete this one, and I go drag Freddy in there. You look young, Freddy. '54. Quite a young picture of you. Is it right? No? Okay. I guess it's an old picture because you really look... But you see how easy it is actually today to use it. And if you say, I copy this image and I process it again in this, but now I ask not only HNet to process the image, but give me the probabilities. And then it gives the probabilities. The probability that you are 45 is very small. Well, you cannot see all these numbers, so let's make a list plot. This is a list of numbers, and I want to have a plot of all these probabilities. You tell them filling to the axis, and you'll see what it does. Well, all the points are now filled to the axis, and you get a really nice plot. So you see how easy it is to program. You just tell what you want. Plot the probabilities, tell them that you fill them, and you get it really nice, and it's extremely complete. If you want to have the mean, you just say calculate the mean, and then you have the mean. This is more precise. And if you take the maximum value. But let's see when it goes wrong. So suppose I take an image that is not so much focused on the image, but there's a lot around it. And you very well recognize this person, the Pope. And now we say, okay, we call this image, and that's now all these pixels. And we say, now do HNet is right here on this image. 52, and that's clearly wrong. And the reason is that this is not how the system learned. The system learned on a face only, not on a face with windows and you name it, the whole context around. So let's first find the faces, and in Mathematica everything is English. So you just say, find faces, and then it processes this image and it says, okay, it's in a rectangle, so show me the rectangle. And this is now where the face was found. And Creddy asked, crop it. Okay, so let's do crop, and that's called image trim. And now we ask Mathematica, crop it. And now we ask, so we say crop is now this image. Let's now do HNet on crop. And now it says the right thing. So this is a very good lesson. It only does what you train it. So if you train it with the wrong data, you get the wrong answers. If you don't train it with, let's say, breast tumors, but you train it with the whole breast instead of that small thing, or you train it with 2 breasts and you ask it to work on 1 breast, it will not work. So it's a lesson. Train it what you want it to do. If you train it on faces, it will only recognize faces. If you want it to train on faces with lots around it, you need a new training. But the human brain has learned all these phases. We have to train this for many, many situations, and the human brain was trained for many situations. If I show you a face upside down, you have never seen a face upside down. You don't recognize it, even it's very familiar, because you have never seen a face upside down. It's coming up later when I talk about human vision. And it's quite impressive how bad we are with faces upside down. We can ask all kind of information from this net. How many connections are there and how many weights, and well, this is not so interesting, but there are 134 million connections in this network. So that's already quite a big network. Okay, I end this very first connection and show you a couple of more networks. Let's go to a few more trained networks. I start Mathematica for it. It's called a notebook. Let's make it a little bit bigger. And I'm going to use a CycleGAN. And a CycleGAN is something that you must have heard. GAN is a neural network that can create something. The G is from generate. It's a generative adversarial network. It can generate faces. It can generate a certain style. It can generate text. It's quite impressive. And this is generating a style. So if I look at what is the description of this network, it turns a photo into a Van Gogh style painting. So it has just learned how does Van Gogh paint. So if Van Gogh has a kind of a corner, how does it fill in the colors around that corner? If Van Gogh makes a triangle, how does he typically do that? And then you can give it an image, and then he paints it in Van Gogh style. So let's load the network. We load and now we have the network again. Let's have a look. Okay, it's a long network again. By the way, if you click on a layer like this, you click, for example, on this layer, 32, you get exactly what this layer is doing. So you nicely see how many pixels go in, how many pixels go out, and you can do this from all the layers, one by one. And that's extremely efficient to see what these networks are doing. And the output is an array, 256 by 256, so that's an image, and it's a color image. So you can quickly see by just clicking on it, what is this layer doing? Okay, let's give now an image that Van Gogh has never seen in X-ray room. That is far too modern for Van Gogh. So I make it the X-ray room, and I have to tell the network a little bit that this is a somewhat more wider image, so I have to learn it that the image dimensions are a little bit bigger. So now I have a network that takes bigger images, and let's actually do it. So we call it Van Gogh Net. It's now processing, and of course it takes some time, but let's do it relaxed. And this is the result of how Van Gogh would have painted an X-ray room. And because every little detail, how he strokes all these things, is in Van Gogh style, coloring, edges, and it's beautiful. So this is now how this computer thing is made. And of course, this is nice for art, etc. It could also be dangerous. Suppose you do this on a breast cancer image, and you get a very strange breast cancer image. You show that to the doctor, hey, this is art, but the doctor may see, hey, yeah, no, I still see something. It's now a fixed command, and it's called image restyle. So you just say to Mathematica, process an image, that's this one, and then learn from the styling types from a small image. And now you see it does something very creative with this. And this is endless. You can now very easily make, and all these things, and in Mathematica, everything is a one-liner. And it's immediately English. You want an image restyle. So all the commands on images begin with image, image resize, image rotate. It's so easy, and that's exactly what it does. And it's fast. It's much faster than Python, for example. It's about 4 to 10 times faster. Let's look at colorful image colorization. My goodness, what a world. Colorful image colorization. Okay, colorization, I understand. That means give an image colors. So give it a black and white image, and let's see. Resource object means give me the data from this network, and it says, okay, it is trained on ImageNet, that's the 1.2 million images, and it had 1,000 classes of objects. So this is the famous learning set from that competition that I told you in the beginning. So it has learned about dogs and you name it. I load the data, so again, real time. And I'm not going to show you all the time, but of course you see it's all this convolution layer and all these layers again. My goodness, a long one. And now I tell it to handle the colors right, and I give it an image. And this image is pure black and white. But it has learned, if I see this type of what's called texture, it must be grass. And grass is never blue. Grass is green. So let's see what does it. It gives beautiful color to images. And this is extremely helpful, and it works very well. So all these old paintings from Stan and Laurel Hardy, very old Charlie Chaplin films, they're now colored in because it used to be endless work to do this frame by frame, but now you can do these 10,000s of frames in milliseconds. You can even determine the geolocation. So I have a network here that's called geotag, And what is geotag doing? Let's have a look. It's trained from Flickr data, 100 million data from all over the world. And it has learned where was the picture taken. And of course, if it was the Eiffel Tower, it said Eiffel Tower in Paris. But Eiffel Tower is obvious. That's very... And you could use any type... If I look at my old holiday pictures, and I forgot, where was it? There's some nice church, a church in a village, and I really forgot, where is it? I gave it to this network. So let's see what this does. And I give it now this famous Budapest building. And it says, okay, this is the latitude and the longitude. This is on the map, the coordinates on the map where it is. That's called a geoposition. And the network was called geotag. You just give it an image. And the nice thing in Mathematica is that you can actually give it an image. You can see it. This is not just some computer code or so. It is really visual, what is what you see. And now you want to have the geographics. That means make the graphics, make it a map. And automatically, Mathematica downloads now the tiles of the map to show where is it. And it's, hey, it's in Bucharest. Well, we all know that, but this is amazingly precise and an amazing, let's say, proof of how well this recognition works. This relates a picture to a location. So you see that you can make all kinds of nice mixtures. It's not only recognition, but it's also where is it? And you can do it when was it? Or it's quite substantial what this deep learning actually can do. And if you make the geo range a little bit bigger, it downloads. Yeah. This is exactly how Google Lens works. And Google Lens has incredibly much more power behind it, but the essence is exactly this. Google Lens works with Google Images. And we all upload images to Google Images. But the modern cameras today, they have a GPS sensor. So they measure where you are. It's the same as in a phone. Your phone knows where you are. Because there's a small sensor, they talk to satellites and they know exactly here am I, if I use the map. And modern cameras have the same. And they burn this in the image. So the image has the location, is it? It's called geotagging. In the image, you burn a lot of information about, even about the camera type, etc. And Google learns from that. And people upload more than 5 billion images per day to Google Photos. So it has an amazing amount to learn, and that's why it's so powerful. And now you see the bigger map, because I have the geo range yeah, this is 1 million centimeters. Or no, I think 1 million meters. Anyway, you see a little bit the diversity of what these networks can do. I take the next one, and now I go a little bit deeper into what happens inside. How do they actually learn? So let's give an introduction to these neural networks as such. It will be part of a new book that I write, called Explainable AI from First Principles. I hope to have it ready in this fall. It may be later this winter. And there's an excellent book that was already there. It's called Introduction to Machine Learning. And this book is fully written in Mathematica, and it explains in detail how this all works. It's amazing. It's really amazing. I can highly recommend for those who like to do a little bit of programming, have a look at it. I took a couple of examples from it. My book is a follow-up on this book, so I go a little bit deeper. This is how to use it. My book goes, what happens inside. So what I go do is a little bit of technology, but it's for you nice to see, even for a doctor, what do these programmers actually do? And I make an extremely small network. I call it a net chain, and I do the same as you just saw. I give it a linear layer, a ramp, another linear layer. So I have just a few layers, very little, and I construct it. Let's have a look. You see, it's a very shallow network, not so deep. And it is not trained at all. It has learned nothing. So inside these connections, they have no value yet. Well, how can a computer have no values? You have to give it some connections. And if it's completely unknown, it is red. That's a highlight. Please train me, because I have no clue what to do. I'm not trained at all. And what you start doing in the beginning is you initialize the net. And how can you best initialize the net? Give it random values. So every is just giving a nonsense value. But now we have something. So if I now look at the network, you see it is no longer red. Everything is now defined, but it is nonsense. There is just... if I show the graph, you see it is a nice connection of all these networks. If you click on it, you get exactly what is this layer doing, what is that layer doing, step by step. It's very interactive to see what happens. And this guy, if I put on input, it is expecting 2 numbers. And the output, it gives 4 numbers. So it is a very simple network. It makes from 2 numbers, 4 numbers. So let's give it 2 numbers. And of course, it gives me now random numbers. It gives nothing. But now we go train it. And then you just say, give it a couple of pairs that you say, if it is 1.5, you should learn that this is represented by 0.8. If you do this with images, and I'm going to do it right away with images, you could say, okay, this image is a horse, this image is that, but now I do it a little bit with numbers. And now you train it, and now you see the training is started. So one by one, it learns all these connections, and of course this takes time, and this is the training process. And at the end, you get a graph, and this is how is the error. And you see the error goes down. So here I have a low error after some training time. If I don't train long enough, it gives bigger errors. So the longer you train it, the better it does it. If I take a more complex network, you get... no, this is a more network that has all kinds of... you can make networks with lots of branches, etc. So it's easy to make all these different networks. Okay, let's now do images. And I'm going to do a little bit of playing with these networks, cut them into pieces and put them together. And I'm going to make a network. I do not immediately go to medical images, but I go to mushroom images and classify which mushroom is it, because that's easier. Medical is so incredibly variable, but it's exactly the same principle. I can do this also for brain tumors or for whatever. So I make classes, and the classes I call by name. So you have Morel, Bolete, and now I can ask Mathematica to do a web image search. Find thumbnail-size images, 50 of them, for all the 4 classes. So now it is scraping the net, and it is, I hope the network works fine. This is a test of, yeah, it is downloading now the first 50 images from all the Morels. And now it is downloading the next set of images. And you see how easy it is to program this. It's just a one-liner, and you can ask for anything. If you want 1 million images, just put in 1 million there, and you need a very fast internet connection. Here it's a little bit limited. The reason is that we all share the same network with all of you, and all your phones are doing something, so I get a little bit I think it's ready. We have a... Okay, these are the last ones. It should be okay. Okay, now we have the images. Let's look at a few of these images. And Mathematica has nicely made these images into what's called a set. It's called an association with a key and a value. So it says, this guy is a Morel, this guy is a Morel with an arrow. So it's a beautiful visual representation of what you really expect it to do. And I have 200 of these images. It takes some time, but the ease with which you do it is very nice. I mean, it's highly visual. This is not just text or images or file names. This is exactly how you like it to be. This is made for humans. And Mathematica is exactly made for humans. So I close it. And now, if you take a random choice, you just get 5 random ones. And if you put it in a dataset form, the command is dataset. And now you have a very nice representation that you can use a slide bar. And if you have millions of data, you just use dataset, and you can very easily scroll through your data. So I go make a training set, a validation set, and a test set. What is that? Well, the training set is easy. I take a whole bunch of these 200 images. Let's say I take 100 of these images, and I train the network with these 100 images. But during the training, I have to look up, is it already at the stage that it is good? So I have to test the network during the training, and for that, I use a validation set. So each time, and from the validation set, I know exactly what is the truth. I know that is this, that is that. So the validation set, and I use 50 of these images to validate during the training, is the network already good enough? And then at the end, I want to see the network is ready. I'm going to test it. And that's the final test. And you see, give it these 50 images, I know the truth. And if 2% is false, is that good enough? Or do I really need to go for 100%? Well, 100% is very difficult. But some networks make 100%. So I divide it now, and you see, just use take list. And I use a network efficient net. It's actually a little bit random. That's a network that's trained on these million images, and I just download it from the web. It's quite a big network, and it has all kinds of, here you see, this is even, it has also blocks with loops inside, so it's a pretty sophisticated network. But we don't care, we just have it now in our Mathematica. It's now loaded on my laptop. And if you want to see the layers, this is how the computer inside has all these layers. You never see this, but it is very nice that you see block 2 is the name of this layer, and this layer is the whole thing, etc. When I want to show the last 8 layers, it's this one. -8 means the last ones. If I take 8, I get the first 8, and now I get the last ones. So now I have the last 8, and you see that is just the very end of this project. And at the output, it gives me what is the network doing. But this network was made, if you look at the output, it gives 1,000 classes. And these classes are all kinds of, here, bathroom tissue, I don't know, things that I don't want. I want mushrooms. So I need to change this network. I don't want 1,000 classes. I just want 4 classes, because I had 4 mushrooms. So what I do is I change the output, and I just say, make it a new decoder in which you say, it's only made for these classes. And it knows classes is that set of 4. So now I do a replace. So now I have done the replace part, and now I have a network. If I look at the output, yes, it gives me only 4 outputs. Because with replace parts, I took my 4 classes and replaced that for the 1,000 classes. So I kicked out the 1,000 classes and I put in the 4. And it says exactly what it is. The labels are Morel, Bolete, Mushroom, and Cantarell. So if I now take the last 8 layers, you see, I have now the last 8 layers, and it still has some things to do. It has to learn because it's a not trained network. I didn't do the training process yet. So let's do the training. And I can do the training on my computer itself, but my computer has a very special other computer inside, which is made for the graphics. It's called a GPU. And the GPU is a very special processor. It's actually a parallel processor. If I want to see, and this processor is programmed with a special computer language, it's called CUDA. Is my computer ready for CUDA? CUDA Q, Q stands for question mark. Yes, so I can run CUDA. Let's ask for some CUDA information about my computer. Oops. Yes, it's an NVIDIA chip. It's an NVIDIA GeForce RTX 2060 chip. And it has a lot of processors. It actually has a core count of 1920. That means this small special chip in my computer has 1920 small processors. And they all work together parallel. And that's quite nice. This is a heavy computer. But this means I can now finally do very quick neural network training. And in Mathematica, it's extremely easy. You just say, target device GPU. It does everything for you. It downloads the CUDA compiler, it makes everything, it's extremely convenient. If I say CPU, actually, I could do that later, it goes really slow. Actually, I could put CPU here first. Let's do the training. Now it loads everything and it starts the training process. And you see, it works. It has now done 7%. And you see the error goes... oh. Well, what I actually want to do is stop this process and run it on my fast computer. Let's see. I have to go a little bit up. It's so heavy that it is busy. I shouldn't have done this. Okay, stop. Let's see if it is. But it's really heavy using my machine now. Yeah, it's so busy. But of course, it will be much nicer if I do the more, now I go to, but the lesson is, it's so easy. It is so extremely convenient, and nobody knows this. It's so amazing. And you don't have to learn the language because it's all plain English. And by using it, you see, the only thing is that it has square brackets instead of round brackets, and that's about all. He does exactly the same as I do. So this is a notebook, and you see we have cells here. This is a text cell, this is a code cell, and this is how you write in Mathematica. So you have documented code. It is code with, so you can do this book. You can just run it directly. You get an explanation of what it is. So let's now run it on the GPU. At this moment, it's installing everything for this big computer. It makes 1920 small programs. That takes some preparation time. And then it will learn faster. And now you see it goes way faster. And this is what I like. Now I can do training in a reasonable time. And Google, Microsoft, Facebook, etc., they have huge storage houses with lots of these GPUs, and they can train a lot. But these GPUs actually made it possible that we have now neural networks. Before it, if you have to train a network and it takes a week, not so many people are interested. Sometimes it took a month. And then, a month waiting for the result, and then the result is wrong. You have to do it another month. But now you can do it 1920 times faster, and this is still a laptop if you have more powerful machines. In my lab, I bought several of these big benches, and then we had 18 of these GPUs in a big array, and that's what I used to do retina recognition, and that was a highly professional deep learning system. And it was only 30,000 euros. And then you had about 25,000 computers, €1 each. Okay, now the network has learned, and it's not perfect yet. I could have learned longer. It said it is 4% error, but it should be okay. So let's take out the resulting network, and this is now my trained network. No red, everything is trained. It gives out an output, and it has 4 classes. And let's put some images in. Image 1, image 2, image 3, and I just put them in there. And it says, Bolete, Parasol, Morel. It does a really good job. And this is exactly the same stages that you do for medical AI. You learn it not with mushroom images, but you learn it with brain tumor images, retina images, breast cancer images. And the more you have, the better, but you have to know what is the truth. So someone has to validate, that's called annotation. You have to give it the right thing. But this is actually what it does. And if you can ask from this network all kinds of properties, how well did it do, and here they are. And one by one, you can see how well did it do. So if I run now the test set, all the 50 images, and I want to see how well does it do. It processes them, all 50, and it says, okay, it's actually pretty good. It has, from the 13 morels, it's found 13 morels, no errors. And you see, actually, everything is all right. If it is a morel, it never said it was a cantarell. So this is a pretty good network. Of course, it's simple, but this is how this is called a confusion matrix. How well does it do? And if you get something else here, it said, okay, if it was a parasol and it said it was a bolete, it was wrong, you can immediately see how often did it find how it was wrong. And this is quite nice. So how do I do with time? It should be okay. Is someone? When should I take for a break? At 12? Okay, in 5 minutes. Let me see. I go do a little bit of data visualization. And what I go do is I go work with some simple images, and I call these images digits. And digits is the most famous data set for all the students. It's called MNIST. So you just ask resource data MNIST and take 1,000 of them and show a couple of these images, and here they are. So every image is a small image of a written digit. And why is this so famous? Because it fits on every laptop. It's small, and you can just learn it. And you tell it, what is this guy doing? It's 28 by 28 pixels. So it's very manageable, very easy to deal with. And you tell it it's a 5. And this was extremely useful. But this is now extremely useful because this is, from that day, used in every postal office to read the zip code and to read financial statements. And nice, Freddie, that you had been pioneering in all this. And if I want to see this in a, let's say, feature space plot, I just ask Mathematica to make a feature space plot. And it learns now a lot of how to can make this in high-dimensional space into a two-dimensional space. And you can now look at this, and you see it can visualize this in groups. All the zeros are now right here. You remember this feature space in the beginning with the black dots and the red dots? Well, you can do a little bit the same. Here are all the ones, and here are all the twos. So you see the grouping is already done, and the neural network makes a kind of a division lines between these groups. If I have the mushrooms, and they're still here. Oh, that's stupid. I shouldn't do that. It's downloading the images again. And I already have the images. But okay, let's give it a few minutes. It's going fast because it probably has a good connection. It downloads now a few sets of these images. And here they are. We saw them before. And now I make a feature space plot of these images. And you see they're not so well grouped yet. They're a little bit grouped on intensity. But if I let them now learn by a network, and the network makes the grouping, so I just say, take this network and use this. So I take from the network all the layers to this one, to the average pool. And here it gives me a big number, 1,200 numbers, which are kind of an internal representation of that thing. It's called a hidden state. And I use that now as a feature extractor. So this network is now used as a feature extractor. And now let's have a look. What does it do? And it processes. And again, everything is real time. And now you see I get a quite nice grouping. All the mushrooms with a head are here, and all the boletes are here. So it's a much better visual grouping. And this you can do the same for all your medical images as well. So now you see a little bit the tools that these computer scientists have. How do you develop these kind of systems? What does it do under the hood? There are lots of other examples. This is, for example, a famous data set, Boston homes. And they have lots of data. Is it a good home? How big is it? How old is it? And hundreds of these data. And if you group them, you can also see as a guy who sells these houses, how many fall in this class that have a nice river view in that price class, etc. So it's used by lots of people, not only doctors, but only people. How can I easily recognize that particular set of homes. It's even so, and this is my last example, if you take images from Beethoven, and here I have Mr. Beethoven, and you can see this is just a computer image of Mr. Beethoven, Ludwig. And now I'm going to make, from this guy, different pictures. And I go make camera positions all around this guy. So these are my camera positions, and I do it in 3D. So here are my, and from all these points around Ludwig von Beethoven, I'm going to take pictures from him. And my computer calculates the pictures. So how many pictures do I have? 450 pictures. So now calculates all these different views. So now it calculates 450, no, in this case 60 different views. And I can view a couple of these views. And while it is calculating, this may take another minute or so, we can nicely see that we have all kinds of different views from Mr. Beethoven, from the top, from the front, from the side. And can I group these images? Yes, Mathematica is now calculating the different groups. And now you see that here we see images from the top, here we see images from the left. It is typically grouping them into things, but the message is you can play with this very easily in just a few lines. And that's exactly what I go much deeper in the next section into what we see inside these networks.